slide. In previous class we discussed about the k-means string algorithm. Whenever we say clustering means, everyone will speak about k-means because of its simplicity, even though it is having several weaknesses. For example, sensitivity to outliers. We have seen whenever due to typographical mistake, if mean is moved to some noise or outlier range, but its impact is there. Its impact is average value is deviated a lot. That's the disadvantage of k-means clustering. In k-means clustering, the other thing is we need to assign the initial centroid. How it is possible? That's the hard fast thing. How many number of clusters are there? You need to tell in advance. How can you tell? Right? In k-mean, say for example in previous class, by taking 10 numbers, I want to divide those 10 objects into 2 clusters. Randomly I took k equal to 2. In fact, in reality that is not advisable. Without having domain knowledge, it's highly impossible for me to assign clusters k. If I am not able to assign k, it is not possible for me to go for next step. That's why I am forced to give blind value k. Right or not? After giving k value, next one is I need to assign what are the initial centroids. Right? Even that is also a random assignment. Initial centroids are often chosen randomly. Yes. Clusters produced vary from one run to another. Exactly. Based on the initial centroids, the cluster outcome will depend. Okay. Whenever I modified the initial centroid, the formation of the clusters will change. To avoid this thing, we are using number of iterations. Number of runs we are using. Whenever the number of iterations are increasing, complexity is increasing. Whenever you will get stable clusters, then only we are stopping. Okay? That is related to the k-mean clustering. But k-mean is partition based clustering. What about the complexity? People used to say k-means complexity is linear. Linear means it depends on the number of instances. Not only that, it strictly depends on the number of clusters, number of iterations, number of objects. Okay, these are the four. Fourth one is the number of attributes. That's a very important concept. Number of dimensions is very important. As the dimensions are increasing, your problem suffers with curse of dimensionality. Complexity increases a lot. That's why time complexity for k-mean clustering is order of LK-ND or whatever it may be. LK-ND, you can give whatever the representation you want. What about space complexity? Even for that thing also, M is the number of points. Yes, number of points are nothing but the data set size and dimensions. Based on how many dimensions, number of attributes. K can be varied. Okay, that is regarding the space complexity and time complexity. Next slide. Strength we have seen, simple to implement. If variables are huge, then k means most of the times computationally faster than hierarchical clustering. In reviewing the types of clustering, yesterday we reviewed the types of clustering. There are 3 types of clustering algorithms. One is partition based clustering, hierarchical clustering and density based clustering. If you remember the hierarchical diagram, dendrogram, only once you need to run the clustering algorithm. How many number of clusters you want? You can get that number of clusters. But running is only once. Whereas in k means, whenever the k value is changed, you need to rerun the entire algorithm. That is a comparison between hierarchical and k means. Faster than hierarchical clustering if we keep k small. Means number of clusters are small, k equal to small. If the data set is 1000 elements, if your k is 3 or 4, then you will get result very fastly. As the k increases, it is also increases. K means produce tighter clusters than hierarchical clustering, especially if the clusters are globular. What is globular? Always k means from round shaped clusters, spherical clusters. It will not support for creating arbitrary shaped clusters. Okay. Next slide, please. Yeah, this thing we have seen. The number of data are not so many. Initial grouping will determine the cluster significantly. And at the same time, another weakness of k-means clustering is order of the output or complexity depends on what way we are giving sequence. Data objects sequence. Don't confuse. Objects are nothing but the instances. Attributes are nothing but the columns. Okay? Based on the sequence of input you are giving, formation of clusters will change. Because average mean value is changing now. Automatically final clusters are also changing. Those are the weakness, strength and weakness of k-means clustering algorithm. Now we can move to hierarchical clustering. And if I want to observe the other points means additional issues of k-means clustering, you need to see this thing. Problems with selecting initial points. How can you select? If there are k real clusters, then the chance of selecting one centroid from each cluster is small. Only k centroids. Chance is relatively small when k is large. Whenever the k is increasing, that value becomes obsolete. The probability is less. If clusters are the same size, then that is the formula we used to have, probability. Okay. For example, if k equal to 10, then probability is 10 power 1 by 10 power 10. Okay. K number and k probability. That is 0.3036. Sometimes the initial centroids will readjust themselves in right way, and sometimes they don't. It is not possible for. Only sometimes it is possible to readjust. Always it is not possible. Consider as an example of 5 pairs of clusters. Next slide, please. Maybe this is not, it will not support for animation. That's why I am not able to show the diagram. Okay. You can download the PPT, existing PPT available in data mining within Kumar textbook. Yeah, solution to the initial centroids problem is multiple runs. Yes, helps, but probability is not on your side. That is not our side, right? Randomly I can select. Based on our random selection, it will change. Initial centroid. Sample and use hierarchical clustering to determine initial centroid. Yes. Select more than k initial centroids and then select among the initial centroids. This is somewhat okay, but people are not appreciating, not getting good results. Post-processing. What is this post-processing? What is this post-processing? Suppose randomly I gave centroids are 4 or 5. Output created 5 clusters. I need to observe after clustering. I need to observe what type of clusters are there. Using cluster evaluation mechanism, or if any cluster with less number of instances, I need to combine. I need to put them in another cluster, again rerun. Okay, that is called post-processing. Next option is bisecting k-means. Bisecting is nothing but the bisecting k-means, another option. There are k-means clustering algorithm, bisecting k-mean. Bisecting k-mean means whenever we feel cluster size is huge, we will divide that cluster into 2 parts. Divide the cluster into 2 parts, sub-clusters. That is called the bisecting k-means. This bisecting is nothing but the combination of k-means and hierarchical clustering. That's why it is advised to visit hierarchical clustering first, then bisecting k-means. Next slide, please. And at the same time, there is one novel concept, not novel concept for your batches, ensembler-based clustering technique. What is that ensembler-based clustering technique? To avoid the empty cluster, and at the same time to overcome the initial centroid problem. To overcome the initial centroid problem. Because nowadays every laptop or each and every computer is supporting with multi-core processing. What you need to do if the computer is dual processing computer, you divide first k equal to 3 clusters, run on one processor, k equal to 4 clusters, run on another processor. Finally you compare what is inter-cluster and intra-cluster instances, or In a high-end language, people used to say SSE, sum of squared error. Sum of squared error. The formula looks like similar to Euclidean distance. Sum of squared error. That is the quality criteria of how clusters are formed. Which cluster, which combination of cluster is giving good SSE, you select that cluster number. Okay. Choose the point that contributes most to SSE, sum of squared error. Choose a point from the cluster with the highest sum of squared error. If there are several empty clusters, above can be repeated several times. We need to repeat with various cluster centers. Next one. Updating centers incrementally means these all are the solutions. These all are the issues of additional k-means. What are the initial centers problem? How to select initial centroids. Next, updating the centers incrementally. What is this incremental? Means you need to have an idea of data set. There are two types of data sets are there. Static data set. Static data set means, yes, data is constant. The entire data set is available at your place. Second one is, yes, can you give an example for that? Sensor data. Or the latest word is data stream. Data stream. Data stream. For example, share market data, sensory data. For every 1 minute, share prices will change, right? For every 1 minute, we will get communication data, mobile call data, call records will change. That's why dynamically you need to update. This incremental clustering helps for such type of data. Incremental clustering helps for such data. In the basic k-means algorithm, centroids are updated after all points are assigned to a centroid. See, after all points are assigned to a centroid, we are performing the changing. Try to recollect our first example with univariate data, 2, 3, 4, 5. After forming the cluster, I am comparing the mean value with another object. Whenever 8 is nearer to this thing or that thing, if 8 is nearer to this thing, then I am putting 8 into this cluster and again recomputing. Right? Means what? After performing clustering only, I am adjusting the central value, or assigned to a centroid. An alternative is to update the centroid after each assignment. That is nothing but the incremental approach. Means, whenever I will put the third object into one cluster, 2 plus 3, 5, 5 by 2, 2.5 is my cluster average instead of 2. With that I need to compare. Means, how much computational burden we are putting on the processor. Means dissimilarity matrix you need to construct every time. Whenever you will insert an object, you need to change. You need to check the dissimilarity matrix number of times. That is a computational complexity. Means each assignment updates 0 or 2 centroids. More expensive. Expensive means what? Yes, computationally more expensive. Introduces an order dependency. Yes, always k-means suffers with ordering capability. Never get an empty cluster. You are right. We can avoid empty cluster problem. Can use weights to change the impact. Because can use weights to change the impact means, while discussing on the types of clusters, I mentioned one point. Fuzzy, no fuzzy. Fuzzy means either 0 or 1. No fuzzy means I can give weight. Each and every object belonging to all clusters. But I am 50% weightage to become first class cluster. But I am 30% weightage to become to the second class cluster. I am 20% weightage to become to the third class cluster. Like this probability or weights we need to assign for each and every object. Okay. Pre-processing and post-processing. You can use pre-processing, normalize the data. Yes, pre-processing, normalize the data. Normalizing. If there is any outs, you need to remove. If it is having any empty data, missing values, you need to remove. Those things will fall under pre-processing. Normalize the data, eliminate outliers. Post-processing means eliminate small clusters that may represent outliers. Exactly. Split loose clusters, that is clusters with relatively high sum of